Hi, this is an introduction to conductance-based models for an excitable membrane. These are models that are typically used to model action potentials as they're created in neurons. Before we get started, there's an introduction that we need. We need a little bit of mathematics that we're going to use as we move through this. And so I want to remind everybody about probably the first differential equation you ever saw, which is a one-dimensional linear model, dx dt equals kx, where x is a constant, which we also call a parameter, which in this case we call the rate constant. And so for this very simple differential equation, what we're looking for are solutions of variable x that depends on t, so we can think of it as being like a function that satisfies this equation, so that when we take the derivative of x with respect to t and plug it in here, it's equal to our parameter k times x itself. Alright, so a function that satisfies this is something like this. X of t equals x of 0. This is our initial condition at time 0, whatever value that is, times e to the kt. And if we take the derivative of this with respect to t, we're going to get this constant times k times e to the kt, which is the same as k times x. This is a particular solution for an initial condition that we have, x of 0. Alright, so when k is less than 0, you guys might remember this from calculus, we have what we call exponential decay, which means if I think about what this function looks like, what our solution looks like, when k is less than 0, this exponential is going to decay towards 0. Alright, so if we were to plot that, just a sketch, schematic, we would get something like this, where if we plot x versus t, for any x0 that we come up with when t equals 0, our solutions are going to approach 0, and that's sort of our long-term behavior. Also, we can think about what happens when we set the derivative dx dt equals 0. That is, we set the right-hand side to 0. What values of x make this 0? What values of x satisfy this equation 0 equals kx? And the only thing that works is x equals 0, so that's our steady state solution. So remember what that means is if we start at x of 0, our initial condition at 0, so at time 0, x is 0, then our derivative is 0, and we're going to stay. Our solution is going to stay at 0 for all time. That's our steady state solution. Okay, so we are going to need to remember this as we move along with this, this little tiny lecture, but I want to point out a few other things that we know. So if the absolute value of k, right, so we're saying k is negative, but let's say that its absolute value is large, then we're going to get a fast change. Our rate constant is very large, and our change is fast. When k is small, we're going to get a slow change. We could rewrite this negative value k as minus 1 over tau, where tau is positive. When we write it like this, then we call tau the time constant. And so the way to think about this is if k is equal to minus 1 over tau, we're still going to have exponential decay. But whereas k tells us the rate that this decay goes towards 0, tau tells us the time that it takes to get to where we're very close to that steady state. Alright, so now let's suppose we slightly change our equation. So we did have dx dt equals kx. Now instead of writing dx dt equals kx, let's write it as k times x minus s. Now here we have two parameters, two constants. We still have our rate constant k, but we have an additional constant s. In this case, if we look for the solution, it's going to look something like this. So it's similar to what we had before. Remember before we had our our initial condition times e to the kt, but now we're shifted by this value s. So when we plot that, it looks something like this. So it looks very similar to our previous set of solutions, but now our steady state is actually at s, right? So if I set the right hand side, dx dt equals k x, the quantity x minus s, if I set that to 0, then now the solution, the value of x that makes that true is s. So whatever this value is s, if we have s as our initial condition, then we're going to stay at s. Our solution stays at s for all time. That's our steady state. And other solutions will approach this value s. So this is going to be really important. Basically, we're going to see a lot of terms in our differential equations for conductance-based models that look something like this. They have some sort of rate constant or this reciprocal time constant out in front, negative value, and then they have something like the variable minus the, a constant or a function, and that's going to serve like a steady state. So when we see something like this, what we know is x is going to approach this value, and it's going to do it at this rate. Okay? So keep that in mind. All right, the next thing that we need is we want to start with some simple ideas about how might we model the kinetics of ion channels that open and close. So we're building up to actually writing down an equation that tells us something about the balance of the currents that help create this action potential. But before we do that, we need to know a few other things, like how could we model these kinetics? So let's assume that we're modeling only one type of ion channel right now, and that we're going to ignore the spatial aspects of this problem. So we can think of it as just a patch of membrane. We have a lot of channels in that membrane. So we're thinking about modeling a relatively large number of channels, where the total number of channels is conserved. That means it stays the same over the course of the time scale of our model. All right, so if we have a large enough number of channels, we can think of sort of averaging over their behaviors, and it's reasonable to assume that the rate of change from an open state for a channel to a closed state and vice versa depends on the number of channels in that state. And so what we're really saying here is if we have a lot of open channels, then more channels can change to closed. If we have a lot of closed channels, we have more available to change to open. If we have a small number, only a small number can change. So it's a very reasonable assumption. So we can think of our states like this. We have a closed state, we have an open state. We have a rate alpha of going from closed to open, and a rate beta of going from open to closed. Now if beta is a constant, alpha is a constant, and they are not functions, they don't depend on anything else, they're just constant, then we would call this a forward rate constant and this a backward rate constant. But in reality, these values can depend on other things, like what is the value of our transmembrane potential. When the potential is different, alpha and beta may be different. They might vary with the voltage. So in this case, we could still think of this as being like a forward rate constant, but it's not constant. It's gonna be something more like a function that depends on V in this case. All right, so that's what I point out here. These may be fixed or can depend on voltage or something else. All right, so what we really want is a model that's generalizable, where it doesn't depend on exactly how many channels we have. So let's let N be the total number of channels and N naught be the number of open channels. In that case, we can think about F as N naught over N, the fraction of open channels. So F is going to be a value between 0 and 1. And we don't really care exactly how many channels we have. What we care about is how many of them are open. And so if a lot of them are open, then F is going to be close to 1. If not very many are open, the number of open channels is small, then F is going to be close to 0. And if we know F, then of course, the way we've set this up, 1 minus F is going to tell us the fraction of closed channels. So we're always going to know the fraction of open channels and the fraction of closed channels. Okay, So let's set up our model for the kinetics that tells us something about this fraction of open channels. So we want to see how the fraction of open channels will change over time. And there are only two ways it can change. So one way that F can change is that we have closed channels moving to open. So F will increase. The rate for that happening is alpha. All right, so that's what we see here. Okay, so this depends on this assumption we had that the rate depends on the number in that state. Okay, so the rate here is alpha. This increase in F is going to depend on what the fraction of closed channels is. And then vice versa. The other thing that can happen, F can change because channels that were open can change to the closed state. When that happens, it happens at rate beta, and it will depend on the fraction of open channels. All right? This is called the alpha-beta formulation for the kinetics of this, whatever ion channel it is that we're modeling. If I do a little bit of algebra and group my like terms and pull out this minus alpha plus beta, then I can rewrite this equation in a different formulation. Here, I'm going to let alpha over alpha plus beta be this term that we're going to call F infinity. And then I let 1 over alpha plus beta be tau, and so that ends up in my denominator. All right, so this formulation should look familiar, right? This is what I was just showing you a minute ago. We have something that looks like minus 1 over tau times F minus some quantity. All right, so F is going to approach F infinity. Tau sub F is going to tell me how fast that happens. And this F infinity, if alpha and beta are constant, then F infinity would be a constant. Tau F would be a constant. But since I'm thinking of them as depending on the voltage, then these will also be functions of the voltage. So we call this a steady state curve, right? So if we fix the voltage, and if it's fixed in our in the situation that we're modeling, then F is going to approach whatever F infinity of that fixed quantity will be. And tau F tells us how long it takes. All right? Okay, so we're going to use this later on. All right, now we're ready to talk about our current balance equation. So we start with this equation. This is based on Kirchhoff's law. And Kirchhoff's law is basically it's based on this idea that the membrane, which is a lipid bilayer, acts like a capacitor. And so the capacitive current has to balance the ionic currents due to the ion channels and also any other currents that are due to experimental manipulations. Okay, so this I applied here is an applied current, a current that's applied during an experiment, right? Without that applied current, in just its natural situation, our capacitive current would balance our ionic currents. All right, so we know, let's think about this current, this capacitive current. We know a capacitor stores charge when a voltage is applied across it. And from sort of biophysics, even outside of biophysics, just physics, we know that capacitance is equal to charge over voltage. And so typically we would think of capacitance in farads is equal to charge in coulombs over voltage in volts. If we arrange a little bit, we get that charge is equal to capacitance times voltage. And a change in charge will be a current. So if we think about how this charge changes over time, we're going to get whatever our capacitance is times our change in voltage. So for this lipid bilayer membrane, we think of its capacitive properties as being a property of the membrane, and C as being a fixed value. And so our capacitive current really looks like this membrane capacitance times dV dt. All right, so we can put that in our equation up here. Now, what about this part? What about the currents due to the ion channels? Well, we just talked about something that will affect those currents, and that is the fact that these channels open and close. When they open, they let ions through. When they're closed, they don't, and we have to take that into account. So here's kind of a hand-wavy way of thinking about what's going on here, and I refer you to there are lots and lots of texts and other things you can look at out there to fill in the details of this, but I want to give you kind of the main idea. So how are these ionic currents created? And that will help us understand something about how we might model them. Okay, so let's start by thinking about a non-permeable membrane. All right, so we have a membrane that divides extracellular space, the space outside the cell, from intracellular space, the space inside the cell. And we have a voltage, like a potential outside, and we have a potential inside. And we have ions with different charges outside and inside. So if we have a non-permeable membrane, these ions cannot move across the membrane. And I'm thinking about the size of these letters representing something like the size of the concentration of some particular ions. In this case, for the positive one, I'm thinking about potassium, but in neurons, usually we model what's happening to potassium, to sodium, maybe to calcium ions, and we have to worry about kind of all of that. All right, but in this case, we're thinking about having a balanced situation on each side of the membrane, and if we wanted to talk about a transmembrane potential, which is what we actually end up modeling, and we do that by looking at VI minus VE, the intracellular potential minus the extracellular potential. That's going to be 0. We have a balance on either side, where the positive and the negative are balanced, and so everything's kind of the same. Now let's suppose that we have a non-selective pore. So we have some sort of pore in the membrane that allows ions to go through. We still have this extracellular space, intracellular space. It's non-selective. So the ions will diffuse through that pore in the membrane. This happens due to the concentration gradient, the fact that there, for example, is more potassium, more of these potassium ions on one side. We started out with more on this side than on this side. But so over time, because of diffusion, they're going to even out, right? And everything can be balanced on either side. So again, we have balance everywhere, and our transmembrane potential V, which is VI minus VE, is again going to be 0. All right? In this case, we have no difference in the concentrations on either side. All right, now let's suppose that we have a selective channel, a pore that is selective and only allows potassium to go through. Okay, so in this case, we have two things going on. So assuming that we started like this, right, one thing is the potassium still wants, because it can go through this pore, it still wants to diffuse because of the concentration gradient and even things out. All right? But then once it does that, because this negatively charged anion cannot go through the pore, we start to get a lack of balance on each side of the membrane, right? Because, for instance, now we don't have the same amount of positive and negative ions. Okay, so we still get this diffusion due to the concentration gradient, but now we also have an electrical potential gradient. And so what happens is these potassium channels are going to go through the pore until those two forces are balanced. So now our transmembrane potential, VI minus VE, is going to be less than 0. It's not going to be 0. So that's kind of the main idea about how these currents happen when these channels open and close. All right, so potassium ions will continue to move across the membrane until the concentration gradient of potassium, these potassium ions, is exactly balanced by the electrical potential difference across the membrane. This equilibrium potential, right, where these two forces are balanced, is called the Nernst potential, or the reversal potential. Note that this potential will depend on the ion concentration. All right, so it's going to depend on the ion concentration that we have outside of, inside and outside of the cell. All right, and we can actually calculate what this Nernst potential will be. These brackets here indicate the ion concentrations, intracellular and extracellular ion concentrations for whatever ion we're looking at. We've been talking about potassium, but it could be any other ion. They work the same way. R is the gas constant. Capital T is the temperature in Kelvin. Z is the valence of the ion that we're looking at. So like for potassium, it's +1. And F is Faraday's constant. Okay, so what are the problems here? Well, one is that channels are not always as selective as we would like. And so sometimes they can accidentally let other kinds of ions through. Channel kinetics are dynamic, and so the permeability changes, right? The permeability depends on how many of those channels are open and closed, and we're thinking about what happens when they're kinetic, and they can change. And then another issue in modeling is that there are many different kinds of channels, and so we might have to model a lot of them depending on what our questions are. All right, but what we need for a simple model is some term, I-ion, that captures the idea that our transmembrane potential is going to approach this Nernst potential, and these channels are going to open and close, which will control sort of how fast that happens, whether it happens and how fast it happens. All right, so for this model, we can start by thinking about Ohm's law, V equals IR. If we rewrite it in terms of current, then our current is going to be potential over resistance, right? Another way to think about that is G, or conductance, is the reciprocal of resistance. And so we can think of our current as being our conductance times voltage. And this will help you get the units right if you think about things in this way. So our channels act like resistors. Conductance occurs as ions flow through the channels, creating a current. So here's kind of a general way to think about how we might model this. All right, so we want to have this term minus I ion that will occur in our current balance equation. And we really need a term like this for every single ion. For each of these ions, we know what the equilibrium potential is, what the Nernst potential is. We know that V is going to approach that Nernst potential. And the conductance sort of controls whether or not that happens, how fast it happens. So we need this term to be our conductance. This minus sign out front ensures that V is going to approach V Nernst. Again, this term looks just like the equations that we looked at earlier. So if we think about dV dt, how does V change over time? We have conductance times V minus the equilibrium potential. All right, for this conductance, G bar is a fixed parameter. That's our maximal conductance. That's as big as it can be. If F is the fraction of open channels and it's a value between 0 and 1, then this entire conductance is going to be between 0 and its maximal value G bar. All right, so F here is called a gating variable. It controls the fraction of open channels. We saw how we might model it a little bit ago. And this, this will work for us. It gives us a current. It has the right units. We're able to control the conductance based on the kinetics of the channel opening and closing. And we have this V approaching the equilibrium potential. So in general, right, we have our current balance equation, capacitive current, ionic current, applied current, current applied during an experiment. We already saw that our capacitive current is something like this. We're going to have a sum of these ionic currents, one for each ion channel that we want to model. And then, and we might even have like, two different terms for two different kinds of calcium channels, for example. So it doesn't depend on the number of ions, it depends on the number of ion channels. All right, and then we have our applied current. And keep in mind, for each of these gating variables that appear in this conductance, we're going to need an equation that says how that fraction of open channels changes, and it's going to depend on some function f infinity, tau sub f, and these are most likely going to be functions of our membrane potential, functions of V. They can be functions of other things. Now, for this conductance, I've shown it with only one gating variable. Sometimes you need more than one gating variable. Sometimes you need the gating variable raised to a power. Usually the way you figure that out is by doing voltage clamp experiments, seeing what your currents look like, and fitting this F infinity and tau sub F to the data so that you get channel kinetics that look like the channels that you're seeing in an experiment. This is exactly what Hodgkin and Huxley did. They were the first ones to create a model that looked like this, that used this formalism. So this is often called a Hodgkin-Huxley type model. And they wrote a paper in 1952 where they created this Hodgkin-Huxley model based on doing experiments in squid where they recorded from the giant axon. Note that the axon is giant, the squid is not giant. So you should always say squid, giant axon. Okay, so they received the Nobel Prize in 1962 for this work, and here's essentially what their equations look like. All right, so here's their current balance equation. Capacitive current. This is a current due to the sodium channel. This is a current due to the potassium channel. This is what we call the leak current, and this is the applied current. All right, so if we can block, pretty much all the channels, then we might still see this leak term. Notice that we have this fixed maximal conductance for the leak, and then V minus V leak. This is linear, and typically this G bar L is very, very small. So what this does is it says, if I didn't have the sodium and the potassium currents, then V would approach VL very slowly and I can actually write down a nice analytical solution that looks like this exponential decay. But of course in practice we have Hodgkin-Huxley showed you can model excitable membrane and model these action potentials with just these two additional extra terms, one for sodium, one for potassium. For the potassium channel, this current relies on one gating variable N that you see here. It has this, you can write it with this N infinity tau sub N formulation, or you can write it in its alpha beta form, But either way, you have this N, which is your fraction of open channels, to the fourth. Now remember, N is between 0 and 1, so N to the fourth is also between 0 and 1. They came up with that exponent just based on matching the data. Then for the sodium channel, they needed two gating variables, M, which is raised to the third power, and H, and you have similar equations for M and for H. And again, you can, if you read their original paper, they're in the alpha beta form. This form is nice because if you look at, if you plot M infinity, if you plot tau M, you can get a sense of the dynamics of the gating variable without doing much work. All right, so what happens if we actually simulate this? If we look at what happens for solutions to this 4-variable system, what we will find if we plot V versus time is that we have a negative resting potential. So when nothing's going on, there's no action potential. This is sort of a steady state that V is going to go to over time. One critical thing is this reversal potential for sodium, the Nernst potential, is a high value of V, and the Nernst potential for potassium is a negative value of voltage. All right, so what happens is when the sodium channels have a high fraction of open channels, so M cubed H is close to 1, V is going to approach V and A. When that happens, V is going to increase up towards this high value of V and A. But once that happens, then these open channels, because of the kinetics of these equations, these open channels will change state, and many of them will close, so that this term is close to 0 because M cubed H is close to 0. When that happens, the potassium channel is open, and N to the fourth is becomes closer to 1. Okay, so it starts out with V trying to go up to the reversal potential for sodium, but then the potassium current starts to have an effect, and it's an outward current. Potassium is leaving the cell, and so that depolarizes the cell. It brings it down to VK, this negative value, and that is this sort of recovery from this increase. So we have this increase, depolarization, decrease, hyperpolarization, and then we see that our solution is going to approach the resting potential again. And that's how an action potential happens. All right, so again, sodium current, an inward current, positively charged sodium ions moving into the cell, increasing the membrane potential, depolarizing the cell, we say, because it increases V. When IK, the potassium current, is having an effect, that's an outward current, potassium ions leaving the cell. This is a hyperpolarizing current. It has a decreasing effect. It decreases V. All right, and that is conductance-based model. That is the Hodgkin-Huxley model.